I'm going to introduce our programs director, Sandy Messick, and she will introduce our speaker. So, Sandy, we are recording the presentation, but if you want to introduce our program for tonight, please go ahead.
Thanks, Rich. Can you guys hear me?
Yes.
Okay, cool. Those of you that have been around a while might remember that Clif Ashcraft presented at LVAAS, I think it was February 2020, just before we went into COVID lockdown jail. And I think Cliff at that time talked about his observations of Mars during that opposition. And I really wanted to get Cliff back because I think he's actually one of the most accomplished amateur astronomers that I've met. And I've met quite a few. So according to Cliff, he became an amateur astronomer almost 80 years ago when his mom let him stay up past 11 p.m. to watch a total lunar eclipse. He went to high school in Loveland, Ohio, got his BS in chemistry from the University of Cincinnati, and his PhD in organic chemistry from the University of California at Berkeley. So after doing that, he went to work at Union Carbide, and for 40 years, he did work on polymer synthesis and all kinds of other things that I can't begin to understand or relate to you. I'll leave that up to Cliff if he wants to discuss that. And all that time, he was an amateur astronomer, and he retired, I think, in 2003 and became a full-time amateur astronomer and telescope maker. And behind him, you can see his 7.25 f14 Schumann telescope, which I think Cliff can explain in more detail, but it's an awesome planetary kind of folded refractor design. And he also works with a C11, a C14, and a 12.5 Newtonian at observatories at his home in New Jersey. And those of you that might feel inclined, look for him on Facebook because he's been posting a lot of images recently of Jupiter and Saturn, maybe. I'm not sure if I saw one. Yes. And they're just outstanding images taken from New Jersey through that Schumann telescope. So I think I'm just going to go ahead and turn it over to Cliff. And Cliff, thank you for coming back to talk to us.
Well, thanks for inviting me to come back. It's always fun to talk to you folks. And tonight, I'm not going to talk about Mars, and I won't be using the Schumann medial, which is behind me. That's my planetary telescope. But I'm going to be talking about double stars and a way to get ultra high resolution measurements of double stars in spite of the terrible seeing that we get from near sea level. I'm going to share my screen right now. Hope you folks can see that. Start the presentation. So my talk is on Speckle interferometry of double stars. And most people don't know what in the world Speckle interferometry is, but I'm going to tell you all about it. By the way, that's my Cellestrade C11 Edge HD, which is a regular Schmidt-Cassegrain, but with a corrector lens in the baffle tube that gets rid of the last bit of coma that a Schmidt-Cassegrain normally has. Well, anyway, I'll give you some background to describe how I ever got involved with this in the first place. Well, I have been interested in double star observation for some time now, and I had published papers in the Journal of Double Star Observation on my measurements using conventional charge-coupled device camera imaging of doubles. I had an S-Big ST8, which seems quaintly antique these days, and I did my observations with my 12.5-inch Newtonian. I was a member of the Yahoo group on double stars, and I read it regularly, even when I wasn't making measurements of double stars. And at the same time, I had been doing planetary imaging by the lucky imaging technique using low-cost but high sensitivity CMOS video cameras. Basically, fancy webcams. Now, I came upon a series of posts on the Yahoo group by a group of amateurs who were working with Russell Genet of the University of Arizona on making double star measurements by Speckle interferometry. Now, Russ had access to some very expensive camera equipment that us amateurs would really never get our hands on, something called a electron amplified or electron multiplied charge coupled device camera, and access to 2-meter class telescopes and a bunch of amateurs working with them. Pretty good pro-am collaboration. Well, they were discussing recent exciting developments in low read noise CMOS detectors that might make it possible for amateurs to get into Speckle interferometry. And they were preparing to propose this in a paper they were writing for a symposium in Barcelona, Spain on double and multiple star systems. Well, they thought that the ZW optical ASI 224MC camera might be great for this based upon its very low read noise of about 1.5 electrons, which is like 1/10 what my SBIG ST8 was. Well, coincidentally, I had been using that camera for 6 months already for planetary imaging. So I put my 2 cents worth into the discussion and volunteered to use my camera to try this out. It was several months before the symposium at Barcelona, and they thought, hey, this is a great idea. If it works, we could, change the flavor of our paper quite a bit. So when I tried it on double stars, using software that one of the members of the group had written, it turned out that it worked beyond their expectations, and they put me on the paper as a co-author, and they changed the title of the paper from, hey, maybe it'll work, to, gee, it worked, So this was the title of the paper that they presented, and it got published in the Journal of Double Star Observations as well. Well, you might wonder, why bother with double stars in the first place? Sure, some of them look kind of cool. I mean, Alberio is just beautiful. But why make measurements of them and spend a lot of time working on them? Well, double stars orbit each other in accordance with Kepler's laws. If you observe them over a long enough time, you could determine their orbital periods. From their periods and their distance and their orbital separation, you can actually weigh the stars. The mass of the stars is fundamental to any astrophysical understanding of how stars work. And of course, here is Kepler's third law, where the cube of the semi-major axis, the separation of them, divided by the square of the period, is proportional to the gravitational constant and the mass of the star. You can usually neglect the mass of the minor star. You certainly can in the case of a planet, but you can directly weigh the star just by observing how long it takes to go. They take to revolve around each other. Well, the period and the separation are related according to that law. Now, at typical stellar distances, binaries with wide separations, so you can see them and measure them easily, they have periods lasting hundreds of years. Life is too short to get much information for them. I mean, there are plenty of double stars that people have been observing for, hundreds of years, and they still have only completed a small fraction of one orbit. The closer the binaries are, the shorter the periods, and you get more bang for the buck observing very close binary stars. It takes less time to get the data out to compute an orbit. Trouble is, the closer they are, the harder they are to observe. Atmospheric turbulence limits the resolving power of Earth-based telescopes. That's why we put the Hubble up into orbit. It's above the atmosphere, and seeing is way better up there. Now, If binary stars are much closer than 1 second of arc, they are almost impossible to measure. And the problem is worse for even closer ones. Now, what are the different methods that people have observed double stars? Well, naked eyeball. Hey, that star looks like there's two of them really close together, like probably the ancient astronomer observers noticed the Alcor and Mizar. You could a real good eye test if you could resolve them, and Epsilon Lyrae. Uh, Visual telescopic observation comparing the apparent size of the stars with separation and estimating the position angle just by eyeballing it. That's what William Herschel did. And he got some of the earliest measurements of double star separations and position angles. But it's very poor because the star size depends upon both seeing and the aperture of your instrument. Well, in the next generation, John Herschel, his son, began doing visual measurements using micrometers of various size, like the filar micrometer. Now, of course, this was limited by seeing, the size of your telescope, aperture, visual acuity, and how good you got at doing it. Now, this method was used to build the database upon which the Washington double star catalog is actually based. It's not accurate for sub-arc second separations, though, and most of these stars that we've only completed part of one revolution are in this category of the early ones measured by filar micrometer methods. Spectroscopy is great for observing periodic shifts in the line frequencies caused by Doppler shifts due to orbital motion. It's really great for very close doubles with very short periods. And astrometry of CCD image. Now, this is the method that I and a number of my colleagues used for measurements in the 1990 to 2015 time frame. One of my papers is in the Journal of Double Star Observations, Volume 3, Number 2, Spring 2007. Now, of course, this is limited by seeing, particularly the seeing blobs you get from the couple-minute exposures you need to take with the CCD to see the fainter companions. It's limited to several arc seconds of separation. And finally, we have Speckle interferometry. Now, this has traditionally only been used by professional astronomers, usually at the U.S. Naval Observatory. It's excellent for sub-arc second separation, and it bridges the gap between the visual micrometer measurements and spectroscopic data. But the trouble is, the cameras you need for this are very expensive. You need big telescopes, and but it is limited only by the theoretical resolving power of the telescope. Recent availability of low read noise, low cost CMOS video cameras makes this now a method that we amateur astronomers can use. Check out my papers, Journal of Double Star Observation, March of 2016. And of course, we've got astrometry by all-sky space missions like Hipparcos and Gaia. But the trouble is, they only basically detect stars that are doubles. You don't get observations over long periods of time from those. Well, what is speckle interferometry? Well, it's a way to observe double stars that are way too close to be resolved by ordinary optical observations in the presence of a turbulent atmosphere. The atmospheric turbulence breaks up a star image into rapidly changing blobs of points called speckles, each one of which is an image of the star formed through subaperture lenslets of air called Fried cells. They're little bubbles of slightly different refractive index moving in the atmosphere in front of your telescope's aperture. Although you can't see it, all the information about the separation and the position angle of a double star is present in these speckles, and can be extracted if you do a lot of math and computer processing. It could normally only be done with very expensive cameras, 2-meter class telescopes, mainframe computers, way out of the reach for amateurs. Well, I could show you what's involved. This is a typical binary star. It's WDS 231033229, otherwise known as BU 385AB. That's a more personal identification. It was discovered by S.W. Burnham. The BU is his identifier. And the rest of that tells where it is. It's at right ascension, 23 hours, 10.3 minutes, declination plus 3229. Well, here is a diagram of that star. This is the larger component, component A, and this is component B. And this is the separation between the two, and it's traditionally called rho, the Greek letter rho. And the position angle is measured from the north direction counterclockwise around to the line going between them. And that's traditionally known as
Like
phase.
bugs or what?
Yeah.
So if I were to look at that star with my 11-inch telescope that I had managed to attach to the side of the Hubble Space Telescope in orbit, this is what it would look like. You would see the diffraction pattern from the two stars, and they would be separated by the separation, and that would be very easy to measure with a Fowler micrometer. However, from my location in New Jersey, this is what that star looks like. And that mess dancing around in the field of view there, that is multiple little images of the star. This is twinkling we're looking at, and the result of poor seeing. This is near sea level from my observatory in New Jersey. Now, if you take thousands of images of that twinkling mess and play games with the mathematics by taking the two-dimensional fast Fourier transform of thousands of many short exposure images, and then compute the average of the modulus squared, you get something called the PSD, the power spectral density. Now, do not panic. This is how you get the Fourier transform. Each image is a two-dimensional array of amplitudes. All of the pixels are contributing these. You can calculate the two-dimensional Fourier transform of such an image using this horrible mathematical expression. But each point of the transformed image is a complex number. To add insult to injury, we've got imaginary quantities too. Well, the modulus squared is just the a squared plus b squared for each point of the transformed image. You can ignore the math because that's going to be done by a computer anyway. But if you do that, you could take this power spectrum density, do an inverse Fourier transform on it, and you get this funny looking thing called an autocorrelogram. Well, from this diagram up here, you can see that this is very similar to my diagram of the double star system. We have a bright blob in the middle, two fainter blobs on either side. This distance on both sides, that's the separation, and the angle is the position angle. But wait a minute, there's two of them. It might be that, or it might be that. And the reason for that is we lost the phase information when we squared the complex numbers. But this is no problem. You generally know already which side of the primary the secondary is, and if it doesn't, you can figure it out using measurements made by people with bigger telescopes than you got in better locations, or you can do what I do and use my planetary techniques of lucky imaging to figure out which side it's on. Well, what had been needed for speckle interferometry was a $14,000 to $50,000 electron multiplied CCD camera, a 2-meter class telescope, access to a mainframe computer, higher math skills, Fortran programming skills, and this pretty much limited the activity to professional astronomers and their graduate students who had access to all of the above very expensive stuff. Now, most of this work was done by the professionals at the U.S. Naval Observatory, working with the director, Brian Mason, and of course the group of amateurs working with Russ Genet. Well, what works today now? All you need is a $350 CMOS video camera with a low read noise, like my ASI 224MC or the 1600. These have read noises on the order of 1 to 1.5 electrons versus 15 for a not that old CCD detector in my old S-Big camera. Any good telescope, preferably equatorial driven. You could use a 6-inch f8 reflector on a German equatorial mount, or my C11 Edge on a fork that I had been doing some planetary imaging with, or the C14 I've got. I plan to use that. Access to a decent PC with lots of hard disk space, but most of us have those these days. And this is the big critical thing. One of the collaborators of Russell Genet was David Rowe, who's a really top-notch computer programmer. He's the guy who designed that corrector lens that's in the baffle tube of the Edge HD telescopes from Cellestrad and the corrected Dahl Kirkhams that PlaneWave is selling. Very bright guy, and he wrote something called the Speckle Toolbox that does all that horrible math for you. All you've got to do is join the Speckle Interferometry Yahoo group, and I think it's been converted over to whatever it is we're using these days now that Yahoo went down the tube, and download that, or I could send you a copy of what you need to install it on a Windows computer. The resolution you get out of this is limited only by the theoretical diffraction limit of your telescope, which in the case of a 6-inch would be 1 second of arc. My 11-inch that I did this work with, half a second of arc. And the 14 that I plan to do some more work with, 0.41 seconds of arc. And that, people that might have access to a 40-inch telescope, they could have imaged about 1/8 of an arc second separation. Do some really serious work, You don't even need to know what a Fourier transform is. Well, here's the equipment that I used. It's my C11 Edge. It's got an f10 focus, which I amplified up to about f30 with a 3x Barlow lens. It's on a very convenient fork mount. Dew shield, guide scope, which I don't use for this. No guiding involved. A very important element is the video finder. This helps me to make sure I know what I'm looking at. And a motorized focuser is always a great idea when you're doing any kind of electronic imaging with a telescope. It's hard to reach over and work the knobs when you're looking at an image with a crick neck on your computer. And the main camera, of course, is my ASI 224MC. Well, camera calibration is something that you got to do for Speckle interferometry. I don't need to for planetary imaging. By the way, that setup is the same one that I was using for planetary imaging. You have to calibrate the camera. That means you have to determine what the camera rotation angle is with respect to north in the sky and what the image scale is. There's many ways you could do it. You could measure some known double stars and fudge out your camera calibration from that. You could use a coarse diffraction grading. That's what I used for my CCD project with the 12.5-inch reflector. Or you could do drift image analysis. Now, let's talk about that, the best way, drift image analysis. It's built into the Speckle toolbox. It's called drift calibration. What you do is you set up a, come on, play. Where is this? Hang on just a second. There's supposed to be a star image appearing here. Come on, star image. Well, darn. You allow a star to drift across the field of view, and there was supposed to be a star drifting across that field of view. With your telescope drive turned off, and you take lots and lots and lots of pictures. And I'm very sorry you don't see a star twinkling and drifting across. Well, you then run the drift analysis tool in the Speckle toolbox. This gives you a number of interesting plots. A plot of the x-coordinate versus time, the y-coordinate versus time, and from this formula, you could determine how many pixels the star crosses per second of time, and from the relationship between a sidereal hour and 15 degrees at the equator and the declination of the star, you could compute what your scale factor is. And from the plot of x versus y, the slope of that directly gives you your camera angle. And it's returned to you on this little field here. There's the camera angle, there's the image scale, and here's a bigger view of that. This is critical for the measurements which follow. This is an absolute method. It depends only upon the rotation of the Earth, and it's very easy to do using the Speckle toolbox, thanks to Dave Rowe's very elegant programming. Now here's my work process for doing it. I planned the targets for a night run using the Washington Double Star Catalog. From that, I get the right ascension declination of the double star, and the last measured values of theta and rho, etc. That last measure of theta tells me which side of that autocorrelatogram I should be measuring. Run some software on my observatory computer. I usually have Excel or Open Office spreadsheet opened up to have both my target data, time of capture, exposure, etc. I use fire capture for operating the main camera. I have my remote focus software running. I had IC capture running for this particular video camera that was looking through a 70 millimeter telephoto lens to give you a wide field view of the area of the double star, and my favorite planetarium program, Guide 9. That's from Project Pluto. It's a wonderful planetarium program, runs only on Windows, but it has catalogs with it that let you really identify any star with a great deal of confidence. Turns out to be very important for this. So I then do a drift calibration using fire capture and a convenient bright star, turning off the drive temporarily. And at this point, I now get to work. I go to the coordinates of the target star of the planetarium program. I identify to make sure I got the right one. And is there somebody in here? Okay. I use the telescope hand controller to go to the star's coordinates and identify the target by comparing the video finder screen with the planetarium. I use the hand controller to center the target on the crosshairs on my screen from the video finder. By the way, Al's Reticule is a free program that there's a link on Cloudy Nights to. Very convenient thing. You put a crosshairs on top of any program's image. I set the region of interest to a very small area, 256 by 256 pixels typically. Adjust the exposure gain to get about 25% saturated histogram, and capture 10,000 images in FITS format of the target. That usually takes me about 5 to 10 minutes, depending upon the brightness of the star. Identify a suitable reference star, again using the planetarium and the video finder. And by the way, the star better be a single star. You don't want to deconvolute a double star with another double star. Go to it with a hand controller and a video finder and capture another 2,000 FITS of the reference star. Here's what my desktop looks like, by the way. In the background, you can see the spreadsheet that I have been working from. There's a fire capture screen. This is a blow up of that 256 square array that I have a speckle image of the star. And by the way, most of those bright things are noise. The speckle image is this thing right here that you can barely see. Here's my video finder screen, and there right over the crosshairs, that's my target, which happens to be TDT 3890. And here's my guide planetarium screen, my electronic focuser, and the thing I'm controlling this video finder screen with. By the way, here's a blow up of my planetarium screen. The star under the X here, here's all the data on it, including telling me that it's in the Washington Double Star Catalog and it's TDT 3890. So I know this is my target, and I have previously set up the telescope so that whatever is in the center of my video finder is in the center of the screen of my main camera. And of course, here's a blow up of the video finder. I could generally see stars as faint as 12th or 13th magnitude of this. And my work process is to, of course, do the drift calibration, make FITS cubes. A FITS cube, by the way, is just a bag you put images in. It's something I learned from Dave. It's a computer term for organizing these FITS files into a convenient size for operating on. And I take my 10,000 images and I make 10 FITS cubes out of them. And I make one FITS cube out of the 2,000 images of the reference star. And there's a routine for making these FITS cubes. You just tell it where your exposures are and it makes the FITS cubes. Then you process the FITS cubes using another tool in the toolbox on all 11 cubes, the 10 of the target and the 1 of the reference star. It computes the two-dimensional discrete Fourier transform, and you don't need to know what that is. It does the modulus squared, averages over all 1,000 values, and computes the power spectral density of your particular double star. You make the measurements using the speckle reduction tool, which actually converts the power spectral density thing into the autocorrelogram. And you could play with the high pass and low pass filters to get the best contrast so you can measure it the most easily. And you use Ashcraft tool to actually measure the theta and the rho. That is, if you've remembered to type the camera angle and the image scale into the toolbox before you start doing this. Here is a screen of an autocorrelogram. This is just noise around the outside and you ignore it. This is the bright spot in the middle from which you measure either one of these two side lobes with the photometry tool. By the way, here's the tune up of the low pass and high pass filters. Once you make this adjustment for your particular telescope and conditions, you don't have to do much more with that. There is some adjustment of how much you want to use this reference star deconvolution. But here the answer appears in this little field here where you have given it the camera angle and the scale factor. This measurement said the theta was 265.518 degrees, and the separation is 0.4644 arc seconds, which is pretty impressive for an 11-inch telescope. You know, that's a little bit beyond the theoretical resolving power of an 11-inch aperture. And this was based upon measurement of this very easy to see and quantify autocorrelogram. Now I tabulate the results in a spreadsheet, compute averages. You know, I had 10 Fitts cubes, so I get an average of 10 and a standard deviation. And I communicate this with my buddies in the group with Russ Janae, the other people on the Yahoo group, write up papers for the Journal of Double Star Observation, and give talks to interested folks like you. Here's some typical measurements, 2 successful ones and 1 unsuccessful. This one is just too close to be measured. This was something that the Double Star Catalog suggested should be resolved, but it's not resolved now, so it means it's closer than a half an arc second. These were all very good values. These are my measures of theta and rho, and I compute the standard deviation of theta and rho. So those are typical measurements. I keep track of all my data in a spreadsheet, and this was the measurements to date as of when I wrote the paper. I got down to about 11th magnitude at the primary star, of course considerably fainter for the secondary, and my closest separation was around 4/10 of an arc second, and I had some further away that were very easy to measure with this technique. I might have measured these top stars with my old CCD method, but it would have been tough. But all of these stars were down here would be completely impossible to measure, particularly in New Jersey seeing. Here's a paper that we got. I showed you the credits before. They put a picture of my telescope that I used in one of my slides in the paper, and they were really tickled about this particular star, A592. I mean, Russ Janae just almost couldn't believe that I was able to resolve this with an 11-inch telescope. This had a 6/10 of an arc second, and I actually had one that was closer than that I observed. The telescope cost me $359, and they were impressed that this did as good a job as that $15,000 electron multiplied charge coupled device could do. I also published my own paper in the Journal of Double Star Observations with all of my observations, not just the few that they singled out for the Barcelona talk. Here is a plot of my measures of theta versus the last reported value in the Washington Double Star Survey. My suspicion that this A592 one, this variation was due to a couple of nights where the seeing was particularly horrible, and I was even having trouble focusing my images. Here's how the separation varied with my measures versus the last reported value in the Washington Double Star Catalog. And here's some of my typical images from that data set, and I'm comparing lucky image values that I got with my planetary imaging technique with the autocorrelograms from Speckle Interferometry. And of course, if they're very widely separated, actually it turns out that lucky imaging is a pretty good technique also. But when it gets down to the really close values, you begin to wonder, am I seeing it or am I not seeing it? But it is easy by Speckle interferometry. So far, I've got that paper back in 2006 by conventional method. I have stars named after me in the double star catalog now, along with William Herschel and John Herschel and Burnham and those guys. And I contributed to that talk in Barcelona, got to be co-author on their paper and my own paper. So I've measured over 60 close doubles and actually more since then, many of them with separations way below 1 second of arc. More papers in the works. Questions on this, anybody?
Cliff, this is Sandy. I have one. My question is, and this is probably an obvious, easy answer, but just humor me if you will. I assume all this good data hinges on how well your optics are aligned. Is that correct?
Well, if you have a badly collimated Schmidt-Cassegrain, for example, the autocollograms start to look kind of funky. So it's best to have it tuned up as well as you possibly can. And fortunately, my C11 Edge has pretty stable collimation. And with the corrective optics in the baffle tube, there's really very little coma anyway once you've got it, you got your secondary well collimated. It pretty much goes away. My Schuppmann would probably do a really good job, except it's only 7 1/4 inches aperture. But I hope to get some measurements down smaller than, approaching 3/10 of an arc second with my C14, which I've got set up to do this now.
Thank you.
Anybody want to try it? I could hook you up with the software. You don't even have to know how to do a Fourier transform.
If one thing that's bothering me, and I'm a little rusty on my signal processing theory, but it seems to me that there ought to be a way to preserve the side A versus side B, to avoid having that double double lobe effect come out when you pull the result out of the Fourier transform. Can you elaborate on that a little bit?
Yeah, there is another higher order transform. It's like 1 notch more complicated than the Fourier transform is, that allows you to recover that phase information. And Dave has included that in the last version of the Speckle toolbox, and I've actually used that to do Speckle interferometric imaging of planets. It turns out to be not really as good as Lucky Imaging, but I've gotten recognizable images of Jupiter showing the red spot, things like that. But the professional solar astronomers are using this technique to get really high resolution images of the solar surface. The guys out at Bear Lake in California are using this technique to do it. But it's the technique that David used in the Speckle toolbox is really more optimized for point objects than it is for extended objects. It's not as sophisticated as what the Bear Lake people are using, but it does work, giving you just an image of the primary and the secondary, but it takes a lot more computing time. And using the autocorrelograms is actually plenty good enough for routine work, where you already know what the last measure theta was anyway.
Okay, that makes sense.
Yep.
I'm thinking your reason you didn't get as good a result using speckle interferometry on the planets is that the Fourier transform process will amplify any noise at all, even though it's a low noise camera. There's still some noise, and that's probably what's causing degradation compared to looking imaging.
Yeah. And of course, that was what was preventing people from using the regular charge coupled devices for doing this years ago. It wasn't until these very expensive electron multiplied ones were developed to make the signal so much stronger than the read noise that you were able to do it. The cheap cameras, the CMOS detectors, they work by making the read noise so low that the signal you get is strong enough to let you get away with doing all the math on it.
Right.
Yep.
Thank you.
Any questions from our folks at South Mountain?
Yeah, come back to use the microphone.
South Mountain, just wanted to say thank you so much, Cliff, for an awesome program. We don't have any questions from here.
Okay, I have given this talk up at Stellafade a year or so ago. Not last year, that's for sure. But I also gave the talk at Lowell Observatory. So
Definitely very interesting. It's really fascinating when we have it, advances in technology and we find new ways to apply them at amateur budget.
by the way, looking at that galaxy behind you there, Rich, I have just put together a paper that I gave to my astronomy club, Amateur Astronomers Incorporated, using the Sharp Cap live stacking tool to make images of galaxies clear out to the far reaches of the Virgo supercluster using only 10-minute type accumulations of live stacks. This turns out to be really great for outreach, star parties. Instead of just showing somebody that little dim fuzzy you see there, if you use averted imagination, that's M82. I don't see anything. It's that little fuzzy thing. Well, this lets you bring it up and actually see a recognizable image on a screen, and lots of people can look at the image at the same time.
Yeah, it's getting harder and harder to sell the idea that you really need to have your eyeball in front of an eyepiece. The electronic eyes are so much better than the ones we were born with, even when they were in their prime. And as we get older,
Well, my eyeballs are almost 83 years old now.
Yeah.
And now my favorite eyepiece is a CMOS video camera in my computer. So.
Right.
Rich, you did kind of make an implication of what great work we could do with a 40-inch telescope and using this.
we were chatting about the 40-inch a little bit before everybody else signed on, and yeah, there's definitely some interesting things we'll be able to do with that once we bring it online. So
Yeah, and you don't care what the seeing is. Yeah, within limits.
yeah. Mm-hmm.
Yeah, wouldn't it be great to have the resolution of a 40-inch aperture? Wow. Well, the Russell Janae and his buddies, they actually bought a night on the 100-inch telescope to do speckle interferometry.
Wow.
Yeah. Fun stuff.
Yep. Any other questions? I guess if there aren't any, I'll turn it back to Rich. And Rich, do you have any announcements or anything?